And what's that in this animation? You know how fast something is changing at every moment? Actually, R is for the approximate. I had this before, so. Yeah, this one. So we know how fast something is changing every moment. We want to know how much we have at every moment. Okay, we want to know how much we have at every moment. And what's that? Is that A? Have we achieved the goal? Yes or no? Who says no? So we know how fast something's changing every moment. R sub W, right? Yeah. This is the rate of change of sand falling off onto the scale, and we want to know how much we have at every moment. The weight of sand on the scale at every moment. Leo says no. Autumn says no. Why not? An approximate. So we have an approximate. We don't have the actual weight function. That's what we want. Like A sub W. A sub W, not just A. A is approximate. We want actual W. So how is it that we're going to get the actual? So we've got something, but it's really based on a pretty bad rate function, right? Compared to the actual one. She wants to make the interval smaller. So here's the beauty of GC. When you build something like this, you just make the interval smaller. More accurate, but still an approximation, right? Because it's still based on these approximate rates. Okay, how about this? Okay, no, so this is actually interesting. So what's good enough, right? So
now it doesn't have jagged edges, so now it looks like a clear function.
Okay.
Well, it depends on how much your margin of error is. Right. In the situation.
Is this a curve or linear? No, still piecewise linear, but they're so small that it looks curved, right? But it's not quite curved. All right. How about this?
It's still not there. There we go. It's still. Because now it's like basically the point.
So another way you can zoom in is you can hold the shift and make a box. There's still little constant rates, right? There's still little constant rates. This is for delta x of 0.005. So Eunice says, it's good enough. Yeah, so basically, you're going to get to a delta x where that is so small that you can't tell the difference, right? So I'll go back to. So basically, all these constant rates are basically forming the wave function. And now our approximate accumulation function is, where is that? Sorry. So now that I've got the actual accumulation function in black, this mysterious goal that we were after, I have it in black. And so at some point, we just call it good. We call it close enough. And really, we're talking about what now? Given exact rate, we have exact accumulation. So we have so if delta x is small enough, we could write it this way, but we have an easier way to write it. So if delta x is small enough, we could still use this one, but then we have an alternate way to write this. And this is where we've been going this whole time. Does anybody know? What are you thinking of? That's what this thing is, with a really, really small delta x. This is German S, standing for S for sum, right? S for sum, we're summing up. Now instead of having all these constant rates, we're just virtually we have like every single rate. We have every single rate, but we're summing up what? Not rates, we're summing up the accumulation from intervals, MDX. There it is. Look, see? MDX. But it's like all of the rates now, not just chunking it up and getting a bunch of constant rates. We want the continuous rate function for little teeny changes in x, but it's still the idea of summing up little bits of accumulation, m dx. Starting at a, I shouldn't have used x here. So from a to x, but then for a different day, we need a different variable there. Talk about that later if you want to ask me after class. We need something else there. So why in this program do we put so much emphasis on constant rate of change?
What everything is built from.
What's built from that? Integrals, calculus, right? This is the foundational thing behind an integral, is constant rate of change.
Yes.
That we're summing up all these little bits of accumulation for all these rates over tiny intervals. So that's constant rate of change is the bedrock of integration or integral. Ooh, awesome, cool, thanks, Mark. Have a wonderful break.